All right, a few area problems that we're going to end up using factoring to solve. So we've got the altitude of a triangle is 5 less than its base, and the area of that triangle is 42 square inches. We want to find the base and the altitude. All right, so since we've got ourselves a triangle, I'm going to draw everything I know about this triangle and most triangles in general. Okay? So an altitude is the distance from the top point straight down at a 90-degree angle. The base ends up being the side that right angle is attached to. So the pink line is our altitude, while the bottom line then becomes the base. So if I spun my page, even though this line is no longer on the bottom, it's still called the base. If it was upside down, that's still the base, even though it's not on the bottom. It's all based on this right angle right there. Okay. What else do I know about triangles in general? Well, I know that I can find the area of a triangle by taking base times the height, dividing that by 2. I can also find the perimeter of a triangle by just adding up all the sides. So if I call this side x and that side y, the perimeter would be x plus the base plus y, whatever those numbers are. If I look at my picture, nothing mentions the perimeter at all. So that's a little unnecessary fact that I know. But still, it's good to just kind of list everything that we know to give ourselves a game plan. So we're trying to take this equation in order to solve for the base and the altitude, because they're both right there. Base, height, even though kind of different name for it. So when we have any equation, you need the same number of equations as you do letters. So we've got 3 letters, so we should be able to build 3 equations. One of them is right here, so we've already got one of our equations. Our second equation is actually listed right here, that the altitude is 5 less than the base. So the height is whatever the base length is, take away 5. So there's a second equation. So we just need a third one. And the third one feels a little bit like cheating, but it's going to be h is equal to h. Or actually, sorry, b is equal to b. Got that backwards, I apologize. So by doing this, we've got we got our 1, 2, 3 equations. We can also replace a with 42, so that gives us another equation for safe bets. We got 1, 2, 3, 4 of them, so we should be able to solve for both of our letters here. So we're going to plug it in. 42 is the area. The base is just the base. Whatever it is gets to stay. But the altitude is actually base minus 5. So we wrote an equation that we knew about this triangle. We related all the information. That way we could plug all this stuff in to start to help us solve for these 2 numbers, starting with b. So when we do all this work we're about to do, we're going to find the base length. We will then take our base length, plug it in right here, subtract 5, and we have our height. So down here I'm going to put base equals height equals, because that's what we're looking to solve. We can't use the zero product property because we are multiplying, but we don't equal 0. So we might be thinking, well, if we subtract 42, Mr. Carlisle, we've got 0 equals b times b minus 5 all over 2 minus 42. Now it equals 0. Can we use the zero product property? Unfortunately, no. The zero product property only works when everything is being multiplied. So b is multiplying this entire set, so we can disregard that minus sign. But nothing is multiplying the negative 42. So even if b is 0, it doesn't change that 42. Even if this b was 0, or in this case 5, to make it 0, that doesn't change the 42. Because yeah, 0 times b would be 0, divided by 2 is 0, but 0 minus 42 isn't 0. So I'm going to write kind of what that looks like over here. We'll do it again. Say b equals 0. 0 times 0 minus 5 all over 2 minus 42. All of this on the left becomes 0, but 0 minus 42 is negative 42, so it doesn't equal 0. B has to be something else. So because of that, we're not going to do this. We're first going to multiply. Actually, first thing I would do is I'm going to get rid of this 2 because I don't want to deal with that fraction for longer than I have to. I'm going to multiply both sides by 2. That allows me to have 84 equals b times b minus 5. I'm going to distribute, and while I'm doing that, I'm going to subtract 84 from both sides. That gives me b squared minus 5b minus 84 is equal to 0. So now I've got my quadratic. I'm equal to 0. Factoring this down, I'm going to get my two binomials. They're going to equal 0. It doesn't matter what's going on in either of the binomials. This times that equals 0. So the zero product property says this could be 0 or that could be 0. And it works out. There's no like plus or minus some weird 42 like was happening up here. All right, I need two numbers that multiply to negative 84. That will give me negative 5. Oof, tough one. All right. 1 and 84. Definitely not, right? 2 and 42. No. 3, I think 3 goes into 84. It does 28. That's not it. 84 and 4. 84 and, let's try 6. Nope, getting closer though. What about 84 and 8? Nope, 84, I might have skipped it. 84 and 7. There it is. So it is 7 and 12. I need the 12 to be negative in this case. That way 7 times negative 12 is that negative 84. And when you combine that, we get that negative 5. Because a equals 1, we can use our shortcut. B plus 7 and b minus 12. We get b plus 7 equals 0. B minus 12 equals 0. So the base is either negative 7 or positive 12. Well, it's impossible to have a negative dimension. So the base must be 12. Which means, come back up here, 12 minus 5. The height was 7. Now, if we take a second to look at why negative 7 is even considered a potential answer, well, if the base could be negative 7, so over here in pink, if it was indeed negative 7, well, negative 7 minus 5 would be negative 12. Those two multiply to a positive 84. which in the formula for a triangle gets cut in half, we do get a positive 42 out of the deal, but it requires two negative dimensions which don't exist. So that's why it pops up as a potential answer. It just doesn't make any real sense in the context. All right, let's try another one. Each of these ones are much more challenging than any that we'll see on the test. Just kind of help us develop our word problem strengths. So the area and the perimeter of a regular field are 2,000 square meters and 180 meters respectively. So that means area, perimeter. We want to try to find the length and the width. So I've got myself my rectangle right here. What do I know about this rectangle? Length, width, length, width. I know that the area is 2,000, and I know the perimeter is 180. So we need to find length and width, so L and W. We need to have two equations that relate L and W. Well, the first equation that relates L and W is the area equation. But since all I can do is get rid of that A, unfortunately, there is an infinite number of answers that satisfy this problem right here. The length could be 200 and the width could be 10. You know, this could be 20 and 1,000, you know, or 20 and a 2 and 1,000, 20 and 10, or just a bunch of different numbers it could be. So we need another equation that uses length and width, and that's how the perimeter comes into play. So perimeter is adding up all these sides, so L plus L, and two widths. We can replace the 180 and we could take this equation further, dividing everybody by 2. And I think we can all understand what this equation is saying. Take one length and one width, and you'll have 90 meters. So you have half the perimeter when you take half of the sides. So we do have two equations, but they don't help us solve each other. Like, I can't get rid of the L with a number. I don't know the length is 20. I don't know the width is 100. I don't know what those are. But what we can do is use some of our substitution skills from earlier this year. We're going to subtract W from both sides. So that gives us length is equal to 90 minus W. We are then able to take what L is equal to, and we could replace L in this equation right here. We could have also subtracted L and gotten W equals. It's all subjective, kind of whatever we want to do. So we've got 2,000. It's equal to 90 minus W times W. So I distribute that W and subtract that 2,000 at the same time. Kind of save myself some space. I end up with negative W squared plus 90W minus 2,000 is equal to 0. So negative W times W, negative W squared. 90 in W gives me 90 in W. And then I subtracted the 2,000, so that's how it became a negative. Just like with the physics problems or any problems in general, I hate when our first term is negative. So I'm going to divide by a -1. So here's our factoring. I need two numbers that multiply to 2,000 that'll combine to give us negative 90. They turn out to be negative 40 and negative 50. We can use our shortcut since A equals 1. So W minus 40, W minus 50. The zero product property says maybe it's the W minus 40 that's equal to 0. Maybe it's the W minus 50 that equals 0. So we end up with the width potentially being 40 feet or 50 feet. Both of these numbers are valid because maybe the field is longer than it is wide, or maybe it's wider than it is long if I were to turn the field like this. Since it's all a matter of perspective, width could be either of these numbers. When we plug it back in up here, 90 minus W, the length could be 50 or 40. So if the width is 40, then the length's 50, or vice versa. All right, last area problem. Oh, that's kind of cool that my little extra shows up through it, but I don't. That's just going to be kind of distracting. Okay. Last one, we've got a sheet of cardboard. So this is similar like the Amazon problem from class that we skipped over, but if you were to look at Google Classroom at it. So I've got a sheet of cardboard that's 10 inches by 12 inches. All right, so I've got my rectangular piece of cardboard. I'm going to put the 12 right there. I've got the 10 right there. Okay, cool. It's going to be made into the box by cutting equal size squares from each of the corners and then folding up all the edges. So what's going to happen is they're going to cut out squares from each of these corners, which is going to turn that square piece or the rectangle piece of cardboard into like a plus sign, where then if you were to fold it along these black dotted seams right here, you could fold it up into an open box. So this front piece right here, if I kind of have a little dot right there, is that front piece right there. This side right here, I'm going to put 2 dots, is that dot, that side right there. Kind of like dice. It just folds up into a box. They are saying that if the area of the base is going to be 80 square inches, so that's this dotted black line box, so I'm going to draw another one. So the dotted line box, that rectangle right here, is going to be 80 square inches of area. What size squares should each be cut from each corner? Okay, so it's a pretty complicated looking picture, but let's just kind of take a step back and think about what's going to happen. So we've got a 12 by 10 piece of cardboard, and they're going to cut some amount of stuff off of it. So down here, what if they cut out a 1-inch square right here? Okay, so they take 1 inch in and 1 inch out right there. This side goes from being 12 inches long to being 11 inches long. They're going to cut the same thing over here, so it's going to become a 10-inch rectangle. This one's going to become an 8-inch rectangle. We can see that that's going to be the 80 that we expect to see. Let's set up our problem and prove it using factoring as well, because the number I picked is nice, a 1 inch. What if they decided to pick 1 3/4 inch, 2 1/4? We want to have a process in case any number pops up. So we have the 12. after they've taken the corner out, what we're really trying to measure is the distance from here to here after we've cut out the corner. So we're being asked to find this distance in our original picture. Since we do know, but we don't know how much they're going to cut, it's a square, so everything's equal. So 12 minus 2 x's. So the 12 inches that we started with, we're going to take away 2 of how much we take. 1 inch, 2 inches, a third of an inch, a fourth of an inch, an eighth of an inch, whatever it happens to be. Then we're going to find the distance on this side. I'm actually going to put it over here because I have some more room. That was 10 minus 2x. So our base of our box, the length from here to here and along this edge right there, 12 minus 2x, 10 minus 2x. 12 minus 2x, 10 minus 2x. Just like before, there's a lot of information. We're like, man, what are we even trying to do? Well, we're trying to find that area. Well, area is length times width. So we've got 1, 2, 3 letters. So we should be able to use 3 equations or change these letters down so there's only one common letter. And that's actually what we're about to do. Area is 80. Length is 12 minus 2x. Width is 10 minus 2x. We go from having a 1, 2, 3 lettered equation to having a 1 layered equation. This is solvable. I would love to use the zero product property right here, but unfortunately we're multiplying to 80, not 0. Even if I subtract the 80 from over here, that doesn't change anything. I can't determine what this x needs to be in order for everything to equal. So we do have to FOIL this out. We got to multiply our binomials. First, outer, inner, last. I'm going to have to go kind of sideways with this. So we end up with 120 minus 24x minus 20x plus 4x squared is equal to 80. I'm going to combine my like terms and kind of rewrite them. 4x squared minus 44x plus 120 is equal to 80. I always get it to equal 0 before I do any sort of cleanup work. But if at this point you're like, hey, couldn't we divide everything by 4? You would have to divide every number by 4, including the 80. We could at this stage, but I'm going to subtract the 80 first. That's going to leave us 4x squared minus 44x plus 40. I just find it easier to divide 0 by stuff than anything else. It's just one less math problem that I have to think about or grab my calculator in case the numbers are too large. Dividing everybody by 4. Arrives at x squared minus 11x plus 10 equals 0. I need two numbers that multiply to 10. Then multiply to negative 11. That's negative 1 and negative 10. Using our shortcut, our zero product property allows us to say x minus 1 equals 0 or x minus 10 equals 0. So either we need to cut out 1 inch squares or we need to cut out 10-inch squares. Well, if we cut out 10-inch squares, well, what's going to happen is this 10 inch is going to become 0, and then it becomes a negative 10. Just because 10 from that side, 10 from that side. So it's 10 minus 20, which becomes negative 10. That becomes negative 8. Negative 10, negative 8 is still a positive 80. So that's why it pops up as a potential answer. Doesn't make sense when you think about it. So all we have to do is cut 1 inch squares to have a base area of 80. So it feels like it takes a lot of extra steps to do this, but what we're trying to do is take this very well-known equation and plug in all the information that we know so we can figure out what we're being asked to find. In this case, how large are these squares going to be that they cut from each corner? And that is some of the area problems. These are more complicated than the ones on the test, so don't worry about that. But just kind of get your idea of what we're trying to set up, where all the pieces come from, and then we'll work on a few more in class on our review tomorrow.